Hello and welcome back to day 10. You may have noticed there was no video for day 9. It's because I didn't really see there was much TDD to be shown in day 9, so I skipped it. Also, your reminder that for all we know, this may be the last video I make this year. As at some point, the algorithms here are going to become more about the algorithm and less about trying to demonstrate design techniques. So if this is my last video, then thanks for hanging out. But we'll see. And for now, let's just dive into day 10. Okay, so you arrive at the production facility. You feel a nose boop on your leg. A reindeer wearing a hard hat. How adorable. All right, when you open the book, you discover most of it seems to be burned. No. As you're about to ask how you can help, the reindeer brings you a blank topographic map surrounding your area, your puzzle input, and looks at you excitedly. Perhaps you can fill out the missing hiking trails. Topographic map indicates the height at each position using a scale 0 to 9. A good hiking trail is as long as possible and has even gradual uphill slope. That means hiking trails, any path that starts at 0, ends at 9, and always increases 1 for each step. Hiking trails never include diagonal steps, only up, down, left, right. Look up from the map, notice reindeer helpfully you begin to construct a small pile of pencils, markers, rules, compasses, stickers, and other equipment. Thanks. All right. So a trailhead is any position that starts one or more hiking trails. Here, these positions will have height of 0. Assembling more fragments of pages, you establish that a trailhead score is the number of 9 height positions reachable from that trailhead via the hiking trail. In the above example, the single trailhead in the top left has a single score of 1 because it can reach a single 9 in the bottom left. All right, that sounds like our first set of test data. Well, let's go ahead and set ourselves up. We're going to make a hiking map, right? Means we're going to make hiking map tests, right? We're going to go with a theory because we know we're going to do this more than once. So given this data, we expect a score of 1. Calculate trailhead scores. It's going to be our map, and this is what we expect to get. All right, so we're going to want parse the map, find the trailheads, get each trailhead's score. Profit, right? Okay, so that looks like what we're after. So we tend to do, we tend to do our parsing in the constructor. That tends to be the strategy we've taken. And this is a map full of digits. We're going to treat them as ints because that makes them easier to find the next one, right? And to know when we stop. So that looks to me like the usage that we're interested in is the hiking map. Is going to be a new hiking map for the map, right? And then we're going to want to walk the trailheads, right? For our trailhead on in hiking map trailheads. All right. We're going to need a running calculation, so 0. And then we're going to add, or not a runner event sync, that's for sure. We're going to add the hiking map get trailhead score for this trailhead. And we're going to assume that this is a row and a column coming back out of this, which actually means we can just do this row and column. Then we don't have to do that because explosions are good. And then question mark, question mark, question mark, assert equal expected results. I mean, when the underpants gnomes come around and you don't know what the middle step is, sometimes you just have to leave it there and hope for the best. All right, so we know now, based on our API, that we're going to want a list of trailheads. So we're going to say this, public I read only list of row and column. These are our trailheads, which for now is going to be throw, not implemented. All right, and then we also know we want the trailhead score. Let's do public and trailhead score. I said get. I did say get. Get the trailhead score for a row and a column. For a row and a column. Boy, it would be really awesome if I could type correctly. But you know what? I can fix my mistakes just as fast as I can make them. Okay, so if we run this right now, we're going to get our not impls. We're going to throw in here non-invocable. Yes, throw new. Throw a new not implemented exception, please. All right, so there's our not impl. That's great. I'm not going to bother with, hey, I'll just return 1. And then we'll let the next one guide us. We've done that enough. So what we need then is we need a map to be parsed. We said we want this to be ints, so we're going to do this. We're going to say this is our grid. All right. And so our grid is going to be our map. We're going to split you on, We're going to split you on carriage turns and line feeds. With our string split option, remove empty entries, as we have done many times before. And then for the row, for each row item, each node is going to be node minus 0. So that will be convert the character into its integer value. Right, and then we're going to array that. And then at the end of this, we're going to array that. And that's going to get us our grid. We also need to know the trailheads. So we're writing the double for loop that we have written many times before now. Rows less than grid length. Double plus row. Column is 0. Column is less than grid row length. Double plus column if we also know we're going to want to do our famous get grid value for the row and the column equal to 0. Then the trailheads, the trailheads, which we don't have yet, we're going to add the row and the column. So we're going to take this as our trailheads. So a list and not a read-only list, and you'll start out empty. We need to write our get grid value. We don't need to be lowercase about it. It's fine. So get the grid value. We'll drop you right in here. Public int get grid value for row and column. So I'm going to say if row is equal to, is row less than 0 or row is greater than the grid length, or column is less than 0 or the column is greater than or equal to grid row length. We're going to return null, otherwise we're going to return grid at row and column. All right, so that's our please don't throw by going over the edge code that we always use in these scenarios. So we have our trailheads now, right? So this doesn't have to be this. This can just be the trailheads. And then lastly, we need to be able to get the trailhead score. All right, so the calculation for this, when we think about this, is we need to know how many 9s we can reach, right? So given where we are, like the recursion is going to be, we're going to start at 0 because that's where the trailheads are, right? We're going to look left, right, up, and down for 1s. We're going to look left, right, up, and down for 2s. We're going to look left, right, up, and down for 3s, right? So that's a recursive problem. We've been doing a lot of those. So we're going to recurse. Given that, what are our exit criteria for the recursion? The exit criteria is the current spot is going to be the grid at the row and the column. Right? If the current spot is 9, then that means we found a 9, right? Now, we don't have a 9, so we have some other value than 9. We need our friend the directions. So this time, read-only list of int d row, int d column. Directions, this time is going to be easier because we only have to go up, down, left, right. So let's do that. And up, down, left, right. Even though I'm saying those things like that, that is not actually the order I'm typing them in, but you know, that's for you to figure out. Those are our directions. So given that, then we want to say for each direction in directions, and we can deconstruct this into d row and d column. We're going to say next row is row plus d row. Next column is column plus d column. And then we're going to say the next value is going to be get the grid value for the next row and the next column. If next is us plus 1, current plus 1, then what we're going to do is say we need to keep a running tally, right? Result is 0. Result plus equals get the trailhead score for the next row and the next column. And then at the end of this, we're going to return our results. Okay. That looks like an algorithm. Let's see if it's the right one. All right. Still don't know what's here, but hopefully profit comes. Okay, we expected 1, but got 16. That's interesting. All right, let's look at this data. Okay. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Oh, you know what? We're probably counting this 9 16 times because there's 16 ways for us to get to it, isn't there? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. That's another one. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. That's another one. Okay, so that's probably what we're doing. So this counting is actually not the correct score. So we only want to count each 9 that we can reach as 1 point. We don't want to count the number of ways we can reach each 9. Okay, so what's the easiest way for us to do that then? What if instead of returning a score, we return all the 9s we can reach, right? And since we can reach a particular 9 more ways than 1, that probably means what this needs to be is a hash set of rows and columns, right? And this is not a trailhead score anymore. This is a get reachable endpoints, right? So now instead of returning a 1 here, we just have to return ourselves. And then this result is not going to be a number. This result is going to be the new hash set, right? And then instead of this adding up numbers, we're going to do result. We're going to do add range. Oh, we're stealing another new XUnit internal thing. Great. So we're going to add range of these. This implementation of add range is exactly what you'd expect it to be. For each value in values, add it to the hash set. Okay, so stealing another XUnit internal thing. That should get us, because of hash set, all the 9s we could reach. Okay, we got a build error. Where's our build error? Oh yeah, the test is probably wrong. We now need to know how many of these we could reach. We're going to count the items in the hash set. Okay, that looks pretty good. We got 1 instead of 16. That's better. Trailhead in any position that starts 1 or more hiking trails. Here's positions identified to 0. So here's one with a trailhead score of 2. Okay, that sounds good. Inline data. That. Really don't know why that pastes like that. Someday I'm going to ask somebody in the Visual Studio team why. So that should get us 1 9 here and 1 9 here for this one trailhead. So that should get us 2. Let's see if that works. That does. Okay, feeling a little more confident. Positions marked as dots are impassable tiles. To simplify these examples, they do not appear on your actual topographic map. That is true. this is going to be our map. And then this is our big map. Everything's a number. But what we did here when we sort of subtracted from 0, when we parsed everything and gave everything a numeric value, we look at the character map. Dot is 2 to the left of 0, right? So that means all those will come up as -2s. Perfectly fine with that. It's garbage data that's not going to influence us. And obviously hasn't, because we were able to calculate it. Okay, so we have another one here where we have a single trailhead. This is an unreachable 9, but these are reachable, and this one is reachable, so that should be a 3. Okay. Inline data. That'll be 3. And let's run that. It's 4. Did I count the 9s wrong? So there's 3, 4, 5, 6, 7, 8, 9. So there's 2. Oh yeah, there's another 9 here. 3, 4, 5, 6, 7, 8, 9, and 3, 4, 5, 6, 7, 8, 9. Okay, so that's 4. Okay, good. All right, starting to feel confident in this data set. This last piece of data has 2 trailheads, and each has 2 reachable 9s. A trailhead at the top has a score of 1, while a trailhead at the bottom has a score of 2. Okay, so 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. 7, 6, 7. All right, so that's not right. This one can't reach this 9. This one here, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 7, 8, 9. Okay, so that one's got a score of 3. All right, so that's our last piece of data, apparently. Inline data. That's going to have a score of 3. All right, that looks good. So given our real data, here's the larger example, right? So this is our final data. There's 9 trailheads. There are 9 zeros in here. Considering the trailheads in reading order, they have a score of 5, 6, 5, 3, 1, 3, 5, 9, and 5. 3, 5, 3, and 5. Adding these scores together, you get a 36. So this is our data here, right? 8901, 0123. 8901, 0123. So this is this data, which means this should be 36. And that's what this test is. So let's go ahead and uncomment this. Now we obviously need this code. We've obviously, the underpants gnomes have figured out how to turn that into a profit. So we're just going to go ahead and leave that alone. And then the map is actually going to be file read all text from the file name, right? And we should get 36 out of that. And we do. Okay, so when I did this with the big map, this map is decent sized here. It's 45 by 45. Not too huge, so calculation time's probably not going to be a problem. We are anticipating this to just kind of work. So let's go ahead and run this, and it works. Great. Let's move on to part 2. The reindeer spends a few minutes reviewing your hiking trail map before realizing something, returning with another piece of paper, describes a second way to measure trailhead called its rating. Trailhead's rating is the number of distinct hiking trails which begin at the trailhead. So, given this example, let's copy this because I foresee more tests. The above map has a single trailhead. Its rating is 3 because there are exactly 3 distinct hiking trails, right? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, that makes sense. So this, in the old system, would have been a 1, and in the new system is a 3. So they called this a rating, so let's call it a rating. Calculate trailhead ratings map, and then the expected value. Okay, so we have inline data. Well, theory first, and then we have inline data, and then there's our map, and then that we're expecting to be 3. So if we called this with this code, which is of course our old code, which is our score and not our rating, we should get 1, right? Because there's a 0, there's a 9, and there's only, and despite the fact there's 3 ways to get there, we only cared about 1. Okay, so now we've got 3 instead of 1. So what do we want to do here with reachable endpoints? Well, this implementation of reachable endpoints makes an assumption that that it's just, I want to know what endpoints I can get to, but not how many times I can get to it or how many different ways I can get to it. So the easiest way to do that would be to get rid of our distinct that's being done by the hash set, right? So if we replace the hash set with a list, right, then what we're going to see is this test is going to pass because our 1 became a 3, but some of these tests are now going to fail because, for example, this, which we accidentally did the second part first, turned out to be 16. So if we run that and that turns out to be 16, that's telling me that we've gotten in the right direction here. Okay, so there it is. There's our 1 turning into 16. And we don't notice any failures related to 3, which means our 3 worked okay. So I could turn this list into a hash set and then count it, right? So that's one way I could do this here, right? So I could say 2 hash set and then count it. And then that should make all of our tests pass again, right? We have our part 1 tests are failing right now because we're getting 81 and 1110, right? Because they're not hash setting. But interestingly, if we look at 81 and 1110, those are the numbers we're actually looking for. So all we really need to do here is turn this into a hash set, right? And then unskip this and undo this and run this. Now we got 81 and 0. That's, yeah, nope. We actually need the code. The test actually has to be present. And here we don't want a hash set. Here we want just a raw count because that gives us the rating. And now we have all our tests passing. So that's not bad. We could obviously add more tests here. There is more data, right? They give us more examples here, right? We took this example again and got a trailhead rating of 13 because this 0 can reach, each of these 9s, each of these 3 9s. Remember, this used to be 3. You can reach it 13 ways. So like it can reach, this 9 one way, it can reach this 9 one way, it can reach this 9 one way, and it can reach this 9 a whole bunch of ways. So that's how we end up with 13. And then this one's 227. Sure, I mean, we can put all this data in here. This is our again, our normal larger data set where they go through and they tell us that that was 81, and then our huge data set ended up with 1110. And so there you go. Interestingly, like there's not really any optimization that needs to be done here, right? I mean, this whole thing ran in 77 milliseconds. If the map were enormous, there are some things we could think about from an optimization standpoint. For example, this is returning a list. A list basically means we have to calculate all the values ahead of time and put them into one giant piece of memory and then hand the whole thing back. But there is another thing we can do here, right? So IEnumerable in .NET allows you to basically return numbers one at a time without having to put them into a big list. And then there's the promise when you for each over these that you can just come back and ask for them one at a time, and it will calculate each one as you need it. Right? So an interesting way to sort of illustrate this concept is, what if we had, we'll just do this down here real quick, public void fun. All right, so what if we had a generator and we say generate numbers, right? And then we say console.writeLine, the generator, turn it into a list, our numbers. We'll call this numbers. Okay, and we had this function, which was IEnumerable of int generate numbers. Well, we can write a version of this that generates an infinite number of numbers, right? We can say, while true, yield return 0, right? that will never end. I'll give you as many zeros as you ask for. So if I try and run this test, what we're going to see is we're stuck in an infinite loop. We'll never get out of this infinite loop. But interestingly, there are mechanisms in LINQ that, I'm basically going to say for each var number in numbers. Let's do it this way, right? And then console right line the number. And what you're going to see now is you're going to see, let's actually try this. Int value is 0, just to make this easier to see. Right, value plus plus. Okay, so we're going to ever increment these numbers and print them out. So now when we have for each, instead of two listing these things, what you're going to see is that I'm getting numbers one at a time and I'm printing them out. There's no mechanism to say stop. So this will go on forever, although not forever, right? It'll go on until I exceed the value of an int, because that would definitely get it to stop. So let's go ahead and kill this. But there are mechanisms where you can get LINQ to stop, regardless of how long the thing is, right? So you can say where the number is less than 20. And now when I run this, I'll print 0 through 20. Then I think I must have left something else in there. Did I leave the old also? No. Oh, except we need to know when to break out of this for each, right? So the where clause is just filtering out the things, but it's not telling us to get out of the loop, right? We say if, and we're going to put this in curly braces, right? We can now say if number is greater than 20, then break out of the for each. So we print 0 through 20, and then we're done. So even though this thing could generate numbers forever, it doesn't matter because we were able to break out. And there are other mechanisms in LINQ, like, for example, called take. So give me the first 10 numbers, right? That's what take says. Give me 10 numbers and then stop. So that's 0 through 9. Skip the first 3. All right, so now we got 3 through 12. So there are mechanisms in LINQ to take these things that are basically, we would never be able to store every single number ever in memory. But that's okay because this IEnumerable combined with yield return is allowing us to return one number at a time and not the whole thing as a massive list. So if we had an enormous map, then what that meant was we could change this list here into an IEnumerable. And then that way we could process the things one at a time rather than trying to collect them all up into a list at the end. And that's really, the sum total of how it works. That is about it for today, I think. I think we did pretty good on the TDD side. I think we did pretty good on talking about, what might the optimization look like for this if we really need to optimize something bigger. But today they're not asking us to do bigger. Today we were perfectly within our bounds, so there's no reason for us to optimize anymore. But we were able to get both solutions out of a single piece of code. Just by saying, you know what, I'll give you the whole list, and if you only care about counting each 9 once, then you can count each 9 once, and if you want to count all the 9s, then count all the 9s. That's up to you. Anyway, that's going to be it for today. Will there be another one? I don't know. Stay tuned.